Hello, this is my Physics 2211 Oscillations Lab report. The purpose of this lab is to observe the motion of a mass oscillating on a spring and to create a computational model based on physics principles that predicts the motion of the oscillating mass. Then I will compare the observed and predicted motion, and I will plot the energy changes computed in the model. A brief preview of the results is that the model predicts the mass motion accurately. The first physics principle used in this lab is the energy principle, which states that the change in energy of a system is equal to the work done by the surroundings of the system plus the heat transfer. Two other principles used are gravity and the spring force, with their formulas shown in the slide. The final principle used is Newton's second law and the velocity and position update formulas. This is the diagram of the experiment. One end of a spring is fixed while the other end has a mass hanging from it. The mass is moved slightly and then it is let go. The red arrow indicates the force of gravity and the spring force. For this experiment, I chose my system to be the mass, the spring, and the earth. The surroundings are everything else, which includes the air. Some of the key assumptions made are that the only forces acting on the mass are its weight and the spring force, which implies there is no air resistance and no work done by the surroundings. I also assumed that the motion is purely two-dimensional, with no forwards or backwards motion. Another important assumption is that the tracker markings are exactly in the center of the mass. This video is the observed motion of the oscillating mass. I then use tracker to measure the mass position each frame. The initial time is 0 seconds, and the initial position is 11 centimeters to the left of the origin and 64 centimeters below it. The time between frames is 1 over 10.53 seconds, which is approximately 0.0950 seconds. The total time of the experiment was 9.50 seconds, and, as the video showed, the mass follows an elliptical-like path. This section explains how I programmed the initial conditions in the computational model. The mass was set to 0.402 kilograms, and the initial position was set to the previously shown value. The initial velocity was determined using tracker. Delta t was set to 1 over 10.53 times 20, as it had to be a multiple of the frame rate. Then I set the constants to their previously shown values. For the spring, I set the L vector as the mass position minus the spring's position, and S, the stretch, to the magnitude of L minus L0. Then I determined the initial energies of the system using the appropriate formulas. In the iteration loop, the first thing I do is store the initial energies. Then I calculate the force of gravity and the spring force and add them up to get the net force. Then I use the velocity update formula to calculate the new velocity, which is then used to calculate the new position using the position update formula. Then I update the spring using the same formulas from before and calculate the final energies using the appropriate formulas. I then calculate the changes in each individual energy by doing final minus initial, and the total change in energy is their sum. This video shows the predicted motion from the computational model as well as the observed motion. As we saw in the video, the model predicts the observed motion accurately, especially in the beginning. As we can see in the graphs, the x positions seem to slowly go out of phase over time, while the observed y positions seem to lose amplitude over time. As we can see in the graph that shows the energy changes over time, the total change in energy is always zero. However, the changes in each individual energy is not zero, as they oscillate following sine-like shapes. One source of error is not including air resistance in the model, which may explain the differences in x and y position. Furthermore, the experiment only considers motion in 2 dimensions, and the spring is not ideal as it is not massless. There could also be some inaccuracies in the tracker markings. The first additional question asks if the energy principle is satisfied in the model, and the answer is yes. The energy principle states that the change in system energy is equal to the work done by the surroundings plus the heat transfer. Since there are no external forces acting on our system, the work done by the surroundings is zero, and since there is no heat transfer, Q is also zero. This means that the change in system energy should be zero, which is what we can see in the graph. The final additional question asks us to estimate the period of oscillation from the x position and y positions of the data. In the x position, 5 full oscillations are completed in 8.2 seconds, which means the period is 1.64 seconds, which leads to a predicted spring constant of 5.90 newtons per meter. In the y position, 6 complete oscillations are completed in 9.1 seconds, which leads to a shorter period of 1.52 seconds, which in turn leads to a larger spring constant of 6.87 newtons per meter. As we can see, only accounting for motion in one direction is likely not enough to accurately predict the spring constant. Instead, we should use other techniques to find its value.